Hey everyone, we're talking about differentials and linear approximation. And the basic idea here is if I have some kind of graph, like a curve, maybe, like this. Okay, and I know the value of this point, and I want to estimate the value at this point, let's say. Okay, but maybe I don't know the function or something like that. What I can do is draw a tangent line, and so long as it's not too far away from the point, I should be able to use the tangent line to estimate the value of my point here. Okay, so that's the basic idea. So if we go to our notes, here they give us some things that we already know. So this should look pretty familiar to you. It's just a different way of writing our point slope form. Okay, so where this is where we plug in the y value, this is the derivative, this is where we plug in our x value. Okay, so let's take a look at our first example. We're given x squared, and I want to approximate 1.01. So first, let's get the equation of our tangent line. So in order to do that, first I need my coordinate. So I need to find f of 1, which is going to be 1. So my coordinate is 1, 1. Okay, I need my slope, so I need f prime, which is going to be 2x. So f prime of 1 is going to be 2. So I can write my tangent line. And my tangent is going to be, we'll say y equals my slope times x minus 1, and then we're just going to write plus 1 here. So I went ahead and skipped a step. Normally it would be y minus 1 on this side. I just went ahead and moved it over to this side. Okay, so that's part A. Part B wants me to use this and approximate 1.01. So all we're going to do is plug in 1.01 in for x. Oops. Okay, so right here, it's easier if you do not simplify this, because once you get to this step, it'll always be very close to whatever number this is. So here I get 2 times 0.01 plus 1, which is going to be 1.02. Okay, 1.02. All right, so that is my approximation. And now if I actually find the value of f of 1.01, okay, so if I plug this into my calculator, I would get 1.0201. Okay, so what we missed out on is this extra 0.1 at the end, but this was still pretty close. So it was still a good approximation. It just wasn't exact. Okay, so lastly, we want to find our error. So we're just going to take our actual minus our estimate. Okay, so I'm going to take 1.0201 minus 1.02. I'm going to get 0001. So this is my error. And like I said, the error is pretty small, so it was still a good approximation. Okay, now let's actually get into an application. So right here, I want to use a tangent line to approximate the value of the cube root of 127, something that would be rather difficult to do by hand. All right, so what we're going to do is we're going to let our function be the cube root of x, and we're going to choose a perfect cube close to 127 that we know the value of to make things easy for us. So what I'm going to do is, well, first of all, we'll define f of x as x to the 1/3. I'm going to pick x to be 125. Okay, the reason why I'm picking 125 is because it's close to what I want to approximate. Okay, so you always want your x value and the x value that you're trying to approximate to be pretty close to one another. And I know that 125 is a perfect cube. Okay, so first let's take the derivative. Right, so I'm going to have 1/3 x to the negative 2/3. And we could simplify that a little bit. So 1 over 3 x to the 2/3 power. Okay, so here's my derivative. I'm choosing to use x, and so I'm going to go through the same process as before. Okay, so I need my coordinate. So I need to find f of 125, which is 5. So my point is 125 comma 5. I need my slope, so I'm going to plug into my derivative. So I have 1 over 3 times 125 to the 2/3 power, which is going to give me 1 over 75. Okay, so I'm going to now write my tangent. So my tangent is, so I'm going to write f of x here f of x is approximately the value of my tangent, which is my y value, plus my slope times x minus my x value, which was 125. Okay, so this is an approximation of my function at 125. This is my tangent line. Okay, so it doesn't equal f of x, but it should be close, at least, at points near 125. Okay, so now let's actually plug in 127. Okay, so 127, f of 127 is going to be approximately, so 5 plus 1 over 75, 127 minus 125. Okay, so I'm just plugging 127 in for x. So what we end up with is 5 plus 2 over 75. Okay, and so if I get this in decimal form, I get 5.026. Okay, and if you go into your calculator and you take the cube root of 127, it is 5.026, so we were very close. So the cool thing here is that I can just pick a known cube root, use that to make a tangent line, and approximate other cube roots that are very close to it. And obviously you could do this with other functions too, but this is just one application of using tangent line approximations. All right, now let's move on to what are called differentials. Now, differentials in practice, the way we're going to use them are very, very similar to taking the derivative. It's pretty much the same thing as just taking the derivative. Okay, the way we're defining a differential is that the quotient of dy and dx is equal to the derivative. Okay, so this is just different notation from what Newton used. It was two different ways of making calculus. You can look that up on your own. But let's actually go through some examples. So when I'm finding my differential dy, there's a couple ways of thinking about it. Okay, if I take the derivative, then you know that we would have dy dx equals 15x squared. Okay, but I only want dy, so I need to get dy by itself, meaning I can multiply both sides by dx. These would cancel, so I have dy equals 15x squared dx. Okay, another way you could think about it is sort of like with chain rule, sort of. So if we took the derivative, by prime equals 15x squared, and then because of chain rule, I'd have to do x prime, where y prime and x prime are dy and dx. So those are two ways of thinking about it. Kind of more what makes sense to me is thinking about it like this, and then multiplying both sides by dx. So then this would go away. But up to you. Essentially, we're taking the derivative and making sure dy is on one side, dx is on the other side. Okay, so that's my differential. Now what's cool is we can use differentials to help us with things like error analysis and just estimating change and things like that. Okay, so first question, they're saying that a circle is increasing the radius from 10 to 10.1. They want us to estimate how that's going to affect the area. Okay, so what I'm going to do is first write my area equation. Okay, now let's find the differential. So we're going to take the derivative, oops, on both sides, 2 pi r and then dr. Okay, and what I'm going to do here is define a couple things. So what we're saying is that my radius is 10, right? So let's plug that in. Okay, my dr is essentially the difference. It's very similar to delta x. It's the difference between my x values that I'm considering. Now dr is not exactly equal to delta x, but we are defining them to be very, very close. So essentially I can, for all intents and purposes, we can say that they're basically the same thing. And so I'm defining dr to be the difference between my x values, which is 0.1. Okay, and so these will cancel. We end up with 2 pi. Okay, so that is my estimate of how the area will change. So let's actually check our work. So let's find actual delta A, which is the difference of our areas. Okay, so again, my area is pi r squared. So let's find the area with a radius of 10. So that'll be pi times 10 squared, so 100 pi. Now if we evaluate at 10.1, we'll end up with 102.01 pi. Okay, so I want to calculate the area, so I'm just going to subtract these. And I get a difference of 2.01 pi, and this is my delta A. So this is the difference of my areas. That's what delta means. So I get a difference of 2.01. Now my estimate using differentials was that the difference would be 2 pi, meaning that I was off by 0.01 pi, which is pretty good. Pretty good. That's like 0.0314 away. All right, so that's not a bad approximation. All right, let's keep going. Last example. So suppose Earth was a perfect sphere. We determined the radius to be this, plus or minus a give and take an error of 0.1. Okay, and so it's asking what effect this give or take error would have on our estimate of the Earth's surface area. So first, let's define our area. So surface area of a sphere is 4 pi r squared. Now let's take the derivative, or let's find the differential. So dA is going to be 8 pi r dr. Okay, so let's plug in what we know. So 8 pi is constant. My radius is 3959. My dr is kind of like my my tolerance in this case, or kind of like my error, or what the difference could be. It's going to be plus or minus 0.1. All right, so if I plug this in my calculator, I end up with plus or minus 9950.052 miles squared. Okay, so this looks like a really big error. It looks like a really big error. However, if you actually found the surface area, so if you actually take 3959 and plug it in, okay, you'll get an answer of you get a really big answer. You're in the millions, 196 million miles squared. So in comparison to this, it's not actually that bad. My error is only in the thousands. It's almost 10,000. But the area here is in the 100 millions. Okay, so if I were to find my percent error, just by taking my my error here, which I found using differentials, dividing it by my actual value. Okay, so if I found my percent error and multiply by 100, you end up with a percent error of 0.005%, okay, which is very, very, very small. Right, so even though I have potential error of 0.1 miles, that will not affect my estimate of the surface area very much at all. Okay, it'll affect it. I mean, my error, it might be off by a maximum of 0.005%, a maximum of 0.005%. Which is really small, so it's still a really good estimate. All right, so that's it for differentials. I'll see you all later.